Hello and welcome to YCP Chemistry Labs, your College of Pennsylvania's YouTube channel to help get you ready for lab each and every week. This week in the General Chemistry 2 curriculum, we're getting ready for Aspirin Part 1, Synthesis and Recrystallization. This is the first of 3 consecutive labs that we will devote to making aspirin, the same product that you can buy in pretty much any grocery or drug store and many other places. So we're going to learn a little bit about this synthesis and then some of the techniques that we use to analyze not just aspirin but other chemical compounds. So let's dig into what's going to happen this week and get you ready for an exciting, I think, long-term project. 3 consecutive weeks devoted to the same topic, really. So goal number 1 today is to make aspirin. The formal name of aspirin is acetyl salicylic acid. Aspirin fits into the category of compounds that we call an ester, E-S-T-E-R. Organic compounds, for those of you who go on to take organic chemistry, are often grouped together by the important chunks of the molecule, or what we call functional groups, that lend each molecule their specific types of behaviors. All right? So aspirin, or acetyl salicylic acid, is an ester. An ester is a group where you have this going on, essentially. You have a carbon double bonded to an oxygen, bonded to an oxygen on one side, which goes on to a bunch of other stuff, and then potentially on to other things in the other direction as well. So this is an ester, this group right here, where you have, it's a carboxyl group, also attached to an oxygen, single bonded, and then going on to other stuff. So it's internal, sort of in the middle of the molecule. So I guess I sort of misspoke here. If I came back, this would be our ester group right there. Okay. Now, when we make aspirin, it's called an esterification. And one of the most commonly used processes to make an ester is to begin with a carboxylic acid. So this is a carboxylic acid. Okay. So we often begin with a carboxylic acid and or an alcohol, OH, up here. And we're going to split another compound. If you look at this, it looks like potentially 2 carboxylic acids, or it's an ester in 2 different directions as well. And so this molecule will be cleaved and will attach up here at the alcohol part of our salicylic acid. That's what our starting material is called here. This acetic anhydride will cleave and attach up here, giving us the acetyl salicylic acid. We've left the carboxylic acid alone, and we've turned what was our alcohol into our ester here. All right. The other product of this is vinegar. This is acetic acid down here. Again, it's a carboxylic acid as well. You could see the same carbon-oxygen double bond bonding to OH and then going off to something else. So here's your C double bond O, OH, going off to, in this case, a methyl group. All right. That's actually one of your pre-lab questions, so I've just answered a few of the things. Your third pre-lab question for this week is to look at this reaction and, based on what I've described as an ester or carboxylic acid, to circle or highlight the various functional groups, as we call them, the ester and carboxylic acid groups. So you should be all set to do that. Now this reaction takes place with an acidic catalyst. We're going to use concentrated sulfuric acid. That's what H+ is, just a generic way of representing any acid. We're using sulfuric acid. Some of the chemicals that we use are pretty pungent in their odors today. So we want to make sure that we're working in the fume hood, and the fume hoods are on and operating for us. And when you're handling the concentrated sulfuric acid, you may want to wear gloves, although I believe you'll only be using it in a very small quantity, but nevertheless you may want to use gloves during that specific portion of the process. Okay? The reaction itself is pretty simple though. We just combine all of these things in a flask and then we heat it. We're heating it to speed up the process. Roughly, as we've learned from kinetics, every time we increase the temperature by about 10 degrees, we double the rate of any aqueous reaction. And so we're going to have this reaction taking place at about 80 degrees Celsius today. That's a really sweet spot for it. We don't want to go much higher. If you go to too high of a temperature, you might think you'll make it go faster, but some of our chemicals become vulnerable to degradation above that temperature. And so we want to heat it up to get the benefit of having it occur faster, but we don't want to heat it up so much that we destroy our chemicals and ruin the chemistry that we're looking to happen. All right? And this is often the juxtaposition that we have in chemistry. So this reaction is certainly not unique in that regard. Okay? Now when we're done, ideally, if everything went well, we would have our acetyl salicylic acid in our flask, and it would be insoluble in water. So we would add water to the flask, and it would crash out, we say, or crystallize out. However, there's a good chance that not all of our salicylic acid will react during the process today. Maybe we don't let it react long enough. Maybe we haven't heated it up to that temperature high enough to get all of the salicylic acid to react. For a variety of reasons, though, it's often the case that some of your starting material does not react. So this leaves some contaminant in with our product that we're interested in, which becomes really the focus of the second stage of our work and then what we do in the next 2 weeks of lab. So after you make and crystallize your aspirin today, then we want to improve the quality of that aspirin by recrystallizing it. So in this case, we'll dissolve the solid that we collect from the first reaction into a small amount of ethanol, heat it up, and then we will add water again and allow it to very slowly this time form crystals. What we're taking advantage of here is that salicylic acid is more soluble in water than aspirin. So as that water cools down, the acetyl salicylic acid, the aspirin, will want to leave the water by turning into solid crystals. But the salicylic acid, the leftover perhaps starting material, will stay dissolved in the water. We simply pour off the liquid or filter it off, and we'll collect an improved, purer sample of our aspirin by using this recrystallization. Then that's where we'll end today's work, but to set the stage for what you'll do the next couple of weeks then, you'll then set out to prove that that recrystallization improved the quality of your aspirin. Okay? We'll do some qualitative tests that simply show us sort of a yes or no, is our material better or worse, okay? Pre and post recrystallization. And then in the third week, we'll do some quantitative tests. So when it's all done, we'll have a large body of work that will allow us to say, did we successfully make aspirin using this reaction? And how successful were we? How good was the quality of our product by comparing it to aspirin that we can buy at the store? So we'll do that. Same store-bought aspirin, we'll run it through the same set of tests to see how it behaves so that we can then compare it to our homemade aspirin or lab-made aspirin as it is. Okay? Now aspirin is certainly not the only ester that is commonly found in our world. Your textbook has an entire chapter on organic chemistry. I apologize that there is a typo in the pre-lab instructing you to look in chapter 20. That's now chapter 21 since our textbook has been sort of redesigned recently. So chapter 21 in your textbook has information on organic chemistry and organic compounds, and it describes the entire category of esters. So you'll want to look there to get some information about what are some other materials that are esters. You'll find some really interesting common traits, one of which is that most esters have a very pleasant odor as far as most people are concerned. You'll find them in a lot of foods. So when you look through the esters, you're going to notice that several of them are chemicals that we find in fruits and in flowers. Okay? Esters also, though, show up in other natural products. Your second pre-lab question asks you about two specific esters, which are highlighted in chapter 21, or that you could find in an online search probably, asking you to figure out what's in a bee sting, because it's the active ingredient in a bee sting that causes your swelling, and it's an ester. And then what's in, I believe it's in pineapple. Maybe it's jasmine or pineapple. But the pre-lab question has it correctly identified what you're supposed to find. Okay? So the pre-lab questions are really designed to help you understand what esters are, and then to get you ready for making one of the most commonly used esters in the world, aspirin. All right? When you're all said and done today, you're going to have two containers. One containing your raw sample of aspirin that you haven't improved the quality of. You're going to keep a little bit of that. And the other will be your recrystallized. You'll take the bulk of your raw aspirin and put it through the recrystallization process. It's very important that you label these two, that you know that they're yours, and that you know which is which, so that for next week's lab and the following week's lab, you can quickly retrieve your samples and use them for these qualitative and quantitative tests. Okay? A couple of final notes for today. Number one, take good descriptive notes when you can throughout the process. You're going to be asked to, as part of this large formal report that you're doing, to demonstrate that you really did take salicylic acid and turn it into acetyl salicylic acid. A student who's rushing will think that these two compounds are just both white, powdery substances. But if you take anything more than 10 seconds to look at them, you will see significant differences that you can describe and use to make your claim that you successfully turned salicylic acid into acetyl salicylic acid. And so good descriptive notes are important, not just for the salicylic acid, but for the raw and then improved recrystallized aspirin samples. So the more notes you have, the more you'll be able to demonstrate to your lab instructor that you've successfully achieved the goals of this lab. The last thing I would like to urge you to do in this lab is to take your time. Don't rush the synthesis and the recrystallization. I know it's tempting to want to get out of lab and you have many other things to do, but in this case, literally your time is going to decide how good your product is. The longer we allow the reaction to go at that right temperature of about 80 degrees Celsius, the more aspirin we're going to get and the higher the quality is going to be. The slower we let the recrystallization occur, cooling it down from the hot temperature down to the cooler temperature, the better the quality of our aspirin crystals are going to be. And so for those of you who will be doing more chemistry in your future, this is really one of the first chances to learn that good chemistry often takes patience, and it relies on you setting aside that time and observing what's happening with those descriptive notes throughout the process. Okay? So with that, I'll wish you the best of luck in making your sample of aspirin and then analyzing it in the next couple of weeks. I will be back with pre-lab videos for each of those two other weeks of work, so don't worry, this isn't the last time that you'll hear about aspirin. Until then, good luck in the lab today, and I hope you enjoy the experience. Okay, I'm just having a little extra time to cut it out.